class, we were doing several cases of how boundary conditions can be prescribed. And let me also draw the picture of the last example that we were doing. So we have this beam. It's built in at one end. So this is a rigid cylinder, and this is being, displaced axially so that the beam will start to compress. So the motion of the cylinder is prescribed. Motion of the motion of the rigid plate is prescribed. And let us say it is some G naught, okay? The displacement of the rigid cylinder is minus some function G of T E3. And coordinate system, you all know how it is. E1, E2, E3. Yeah, and the other thing is contact between the cylinder and plate is frictionless. Okay, so I think I had asked you guys to think about what boundary condition will be here. Can someone tell me what will be the boundary condition? So at x3 equal to 0 and on lateral surface it is the same as earlier. But at x3 equal to L. Okay, so what do you think? What would be the boundary condition? Okay, so Manu says y3 of x comma t is equal to minus gt. Okay, so let me write down what Manu has written. And I think that is right. So at x3 equal to L, we have y3, y hat, third component for every point at x3 equal to L. So y3 hat of x comma t, that is equal to minus g of t. That's the kinematic boundary condition. And then because the contact is frictionless, and also notice that as the plate pushes the beam, the points on the cross section over there, it's going to radially expand out freely. So the displacement will not be zero in the transverse direction. But it will be such that because of no friction being there, there won't be any resisting force, no resisting transverse load, isn't it? Now the stress tensor there is sigma, and the normal is ny. So we don't know this in total because we don't know how much is the axial component of traction that gets exerted on the beam. We are just prescribing the motion, but we don't know the corresponding load. But we know that in the transverse direction, there will be no traction. So Manoj is very right. So this dot E1 is equal to this dot E2, and that's equal to 0. Now you can see you have three boundary conditions. And because the plate is, it's just moving, it's translating. So Ny will also be equal to E3. You can say that Ny will be equal to E3. Isn't it? So very good, Manoj. Let me, just do the last example. So suppose instead of motion of the plate, compressive load is prescribed, as we had done last time. Compressive load minus P is prescribed. So this is a load that is applied on the plate. So can you now tell me what will be the boundary condition? And again, it is frictionless. Do you think we can say that sigma times Ny, that's equal to minus P by pi r square E3? Would that be right? And of course here, due to kinematics, we know that Ny is equal to E3 here. So this is not right, I must tell you. What is the mistake here? It's very interesting. So as you push the plate with that load P, what do you think is going to happen to the area of the cross section over there? The points on the cross section there are moving radially outward. So the area of the cross section will not remain fixed. It's going to change, isn't it? And we don't know what is the current area. And when you apply sigma, this sigma Ny, it acts on the current area. So it should be divided by, so this should have been the current area. Not the original area. Okay, and that is something. So now can you tell me how to make the correction? Think of using the first Euler-Kirchhoff stress tensor. Can we not say that P times E3, that should be equal to minus P by pi r square E3? Because we know that P times E3 gives you load per unit undeformed area, right? An undeformed area is known to us pi r square. So it is, you see, it is so convenient. With first Euler-Kirchhoff, boundary condition is so convenient, and also you will notice that even if the normal were changing, you won't have to bother if you use first Euler-Kirchhoff because it takes the normal of the undeformed area. In this case, obviously the normal was not changing, but if it were changing, then using using the first Euler-Kirchhoff was much easier. Okay, so this is the correct boundary condition. Any question on boundary condition? So you may also have to, this, for example, is the Lagrangian boundary condition because things are written in Lagrangian variables. But suppose you are solving a problem using Eulerian formulation, then you would have to convert the boundary condition also in the Eulerian formulation. So that is something I leave it to you. You think about it, how you can do that. And I'll certainly ask that in the problem, in the quiz or in the exam. How to convert Lagrangian boundary condition to Eulerian and vice versa. Okay. Okay, so I was asking what would the other two boundary condition here be? So you see, it's a vector boundary condition. It already has three. It has three components. So what we have seen is that whenever you have to solve a deformation problem, you have not just the equations of motion, linear momentum balance, angular momentum balance, mass continuity, constitutive equation. Together with this, you have to also prescribe the boundary condition and initial condition. Okay? Let's move to a different topic. All of you must have learned about work energy theorem in your undergraduate mechanics, work energy theorem. Do you remember that the work done on a system is equal to the change in kinetic energy of the system? And if you have a non-conjugative load also acting, then you have the power form of work energy theorem or the rate form. And in the rate form, we say that the power of external work done on a system is equal to the rate of change of kinetic energy of the system. So I'll just write here, power of external forces acting on a system is equal to the rate of change of kinetic energy of the system. Okay, and this was for rigid bodies when the body was not undergoing deformation. Now let us see how does this look like in the context of deformable bodies. So we can again take a small part of the body, or we can also take the full body itself, but let us start with a small part of the body, any arbitrary part of the body. So that is going to occupy, we have seen that it occupies the region, we call it D ref, isn't it? In the reference configuration and in the current configuration, that's occupying the region dt. Okay, and on this we have body force acting B, and also the traction from the other part of the body, right? Internal traction T, which is a function of course, the point and also the normal. So by the way, I should write that on dt, not on dref, because on dref nothing really is acting. So maybe I'll move them. and put it here. Okay, so for this part of the body force and the traction forces, they are external to it. So what will be the power of these forces? Corresponding to body force, what will be the power? So power, do you guys know what is power? That is force dotted with the velocity of the point of application on which the force is acting, right? So the power of external load, external forces, let us say. So can we say that this is going to be equal to the volume integral over dt, and then we have body force B dot with velocity, and then we say dvy. Can you say that? So body force is acting on every point of the body dot with the corresponding velocity of the point. That's the infinitesimal power, and integrate it over the volume, you get the total power due to body force, right? Likewise, you can also think of the power due to the traction. So that's going to be traction T, and again dotted with the velocity times d, I think we wrote dA, perhaps dAy for the area. Okay, now let's do some mathematics. So why don't we convert this second integral into volume integral? So for that you have to write T in terms of sigma times n, right? So this one is then going to become sigma n dot with V dAy. Okay. All right, and then if you want to use Gauss divergence theorem, bring the sigma on the other side, and you have del dt n dot sigma transpose V. Okay, and this is now in a very convenient form for using Gauss divergence theorem, because sigma transpose V is like a vector. So V dot n dA is simply divergence of that vector, right? So we get volume integral now, and Eulerian divergence dot sigma transpose V dVy. Okay, what after this? Anyone? Anyone knows how to proceed further? Here this velocity is not a constant, it's changing with y, the current coordinate. So how to proceed further? So obviously we don't know. So you have to therefore switch to indicial notation and work out. So let's switch to indicial notation. So divergence with respect to y dot with sigma transpose v. So if you call this a vector A, then this is equal to del AI over del YI, isn't it? Divergence. But AI, what will that be given that A is equal to sigma transpose V? So can we say that it is same as del over del Yi, and AI is then sigma Ji Vj? Can you say that? Isn't it? Because it's sigma transpose into V, therefore we get sigma Ji into Vj, or sigma Ij transpose into Vj. Alright, so then you simply use product rule now. So we have del sigma Ji over del Yi times Vj plus sigma Ji into del Vj over del Yi. Okay. Now this thing over here, we have already seen several times. So this one, for example, that is the divergence, Eulerian divergence of stress tensor sigma and its ith component. Sorry, jth component. We have seen this several times. So that has to be multiplied with Vj. So therefore, this is simply divergence dot with sigma and further dot with the velocity V. Okay. And then the second one, you can see it is sigma Ji del Vj over del Yi. And what is del Vj over del Yi? That's the Eulerian gradient of velocity. So that's your L, isn't it? L, the Eulerian gradient. So this is simply sigma Ji Lji. Okay. And this you can also write as, it's called double contraction. So I think you have seen this also in my lecture. Sigma double contraction big L. So double contraction is when you multiply component wise and just add it. Single contraction, that's the dot product. A dot B is AI BI. And here we have double contraction because you are contracting over both the indices. Okay, so this is how you see we could find out the tensor form of the original operation. It was not easy to see it directly, but when you went through the indicial notation, then you could see what it is. So always, always try to do that. Okay, so this we can now put it here and write it as integral over dt divergence y dot sigma dot with velocity plus sigma double contraction L. Okay, and the whole thing is then dvy. All right, so now let us see the total power. What's the total power then? So total power is now so first one was due to the body force. So we have everything now on the volume. Due to body force, it is B dot V. And then due to the traction forces, we are getting divergence of Y dot sigma dotted with V plus sigma double contraction L dvy. Okay, now comes the real thing. So you can now see it is integral over dt, and look at the first two terms here. it has V as common, isn't it? So you could write it as divergence y dot sigma plus body force dot with velocity plus sigma double contraction L. But it turns out this thing you can also write it as sigma double contraction D, where D is just a symmetric part of L. Now, why we can do that? Let me do a side calculation. This sigma is a symmetric tensor, okay? So why don't I write it as sigma double contraction, and L we write it as D plus W, right? Where D is the rate of deformation tensor and W is the spin tensor. Remember the antisymmetric part of L. So sorry, I think D is called the stretching tensor, perhaps. I forgot the name. So, but D is the symmetric part of L. So just be sure about that. So this becomes sigma double contraction D plus sigma double contraction W. Now W is antisymmetric, okay? Now you see this thing is same as sigma ij Wij double contraction. But Wij is equal to minus of Wji, right? So this is same as minus sigma ij Wji. And then sigma ij is same as sigma ji because it is symmetric, minus sigma ji Wji. But you see this is same as what it is here. Sigma ij Wij and sigma gi Wgi, they are same. It's just like I has become j and j has become I, and they are dummy variables, dummy indices. You can always change its symbol. But what you see is that this is equal to negative of this. So therefore it implies it is 0. Okay. So if you contract a symmetric tensor with an antisymmetric tensor, and you double contract a symmetric tensor with an antisymmetric tensor, you get 0. Okay, a big 0. Okay, so coming back, now what is this thing inside the bracket? Can't you say that this is use LMB, right? It's then rho times acceleration, isn't it? So that's simply rho times acceleration. Okay. Then comes the last resort, of course. So let me see what is this thing over here. Integral over dt rho a dot with velocity dvy. So we are just slightly away from the final result. So this is same as, convert this into the referential integral d ref rho naught, okay? And then acceleration becomes a hat, which is same as v hat dot, right? So I'm just going a bit fast. And then dotted with v hat. And this is then dvx, okay? Which is also equal to integral over d ref, and this is then rho naught. Can we say that it is half of rho naught v hat dot v hat, and then the whole thing you have a time derivative dvx. So this also, then you can bring the time derivative outside also. So this is then d by dt integral over d ref half rho naught v hat dot with v hat dvx. And what is this thing inside the bracket? Can someone tell me what is this thing? Yes? Anyone? Right, kinetic energy of this part of the body. And you see, you can write it in either Eulerian form or in the Lagrangian form. So what you have found finally is that total external power that's equal to rate of change of kinetic energy of the system, right? Something that we saw to begin with. But then it also has an extra term, integral over dt sigma double contraction d dvy. Okay, so this is of course the kinetic energy of the system. So what we see is that in our undergraduate mechanics, we had seen that external power is equal to rate of change of kinetic energy of the system. But now for a deformable body, it is equal to rate of change of kinetic energy plus an extra term. And you see this D is 0 for rigid body. It is 0 for rigid body, and therefore you get back the original result. But if it is deformable, then D is not 0. And this thing is also called stress power. Okay, stress power. This is the power due to internal stress. And this result is again valid for all kind of deformations, all kind of body, whether it is liquid, solid, fluid, whether you have just elastic deformation, plastic, viscoplastic, dissipative motion going on. For everything, this is going to hold. You just need to have a continuum viewpoint of the body. Okay, now this stress power, it's very useful. This allows you to find out what's called this. Sometimes they also say it's work conjugate. There is something called work conjugate stress and strains. Work conjugate stress strain pairs. So for every measure of strain, there will be a corresponding stress. And how are they related? Is by the fact that when you do stress dotted with strain dot, it should give you the same power as here. So I'll illustrate that also. So basically, if stress is denoted by, let us say, I should use something else, no? Suppose I use S for stress, which can be any measure of stress, okay? But S is also, I have used this for second Piola-Kirchhoff. So I should use something else. So suppose I use T for any measure of stress, okay? And for strain, I use for any measure of strain, suppose I use Z, then this T double contraction Z dot, and when you integrate this over the volume, or in fact you can also do localization argument to relate it to sigma double contraction D. So the work conjugates will be such that when you work out this double contraction, it should equal sigma double contraction D. Okay. So let us use this to find out, different stress strain pairs, work conjugate stress strain pairs. So first of all, let me write this down dt as sigma double contraction D, and I want to see what is the work conjugate strain measure for first Piola-Kirchhoff stress tensor, let us say. So this is sigma double contraction D, dVy. By the way, this D is not time derivative of anything, isn't it? D is not the time derivative of anything. So therefore, corresponding to sigma, we don't have any strain measure whose time derivative, when you double contract, you get the power. So I'll just make that remark here, that D is not the time derivative of any quantity. Okay, so anyway, so proceeding further, so we have seen that this is same as integral over dt sigma double contraction L, isn't it? dvy. But this is also same as integral over dt sigma double contraction f dot f inverse, isn't it? That's your L, no? dvy. Okay, now when you work out, using indicial notation, you can bring this f inverse on the other side, but then you get a transpose. Okay, so what I mean to say is that this is going to give you integral over dt sigma f inverse transpose double contraction f dot dvy, and then dvy, why don't I write it? Okay, let me write it as dvy only, and this is then integral over reference region dref, and then you have j sigma f inverse transpose double contraction f dot dvx. Okay, and do you know what is this thing inside the bracket? J sigma f inverse transpose. P, right? First Piola-Kirchhoff stress tensor, right? P, double contraction F dot. So what you have seen is that these two are same. But now this stress power is written as P double contraction F dot. So therefore you can say that P and F are kind of stress strain conjugate. So work conjugate of F is P, or work conjugate of P is F. So this allows you to see this, okay? And you can likewise think of other kind of stress measures also. For example, you have this strain, what is called Lagrangian strain tensor, isn't it? The Green Lagrange strain tensor, do you guys remember what is that? Green Lagrange strain tensor. So that's E, which is half of F transpose F minus identity, isn't it? So if we try to find out what is the work conjugate of E, so how will you do that? So you see, because E is a Lagrangian measure, no? So we should, if we say that the work conjugate of E is some T, let us say, then T double contraction E dot, we have to then relate it to P double contraction F dot. Because E is Lagrangian, so T double contraction E dot is like the work done per unit reference volume. So we have to relate it to P double contraction F dot. Do not relate it to sigma double contraction D, because sigma double contraction D is the rate of work done per unit deformed volume, okay? Whereas P double contraction F dot is rate of work done per unit reference volume. So that's the only difference. So I'll just write here, sigma double contraction D is the rate of work done per unit deformed volume, and therefore it is integrated over the deformed volume. Whereas P double contraction F dot is rate of work done per unit reference volume, okay? So basically P double contraction F dot would therefore be equal to J times sigma double contraction D, okay? So anyway, so now this T double contraction E dot, because E is a Lagrangian measure, so when you dot it, it will give you work done per unit reference volume, and therefore you have to equate it to P double contraction F dot. Okay, now let us see what will this T be. So if we have to find that, put in the formula of E. So you have T double contraction half F dot transpose F plus F transpose F dot, okay? That's it, right? Because identity, when you dot, it becomes 0. And this is equal to P double contraction F dot. Okay, so now we have to think of what is this going to become. So it is then 2 times T double contraction F dot transpose F plus F transpose F dot, and that's equal to P double contraction F dot. So can anyone tell me what we are going to get? So maybe we should switch back to indicial notation, okay, and see what we have. Sorry, it was half, no, it is not 2t, it is half t. It is t by 2. So if I use indicial notation, then we have half tij, and then this thing, ij component, that's f dot kj, sorry, ki into f k j. So ij component of f dot transpose f, that's f dot ki into f kj, isn't it? Then the next one is then tij again, and then the ij component of this thing, that's fki into f dot kj. Okay, and that's equal to pij into fij. Okay, now does anyone know how to move ahead? Fij dot, sorry. So we have to take, f dot outside on the LHS. So how we can do that? F dot outside, and it should be common to both of them. So here, for example, you have this f dot ki. Can I change the index I to j? Okay, let me change the, okay, we can't change I to j because j is already there. So, but if we change I to j, we can change j to I. So here, what I'm going to do is change I to j and j to I. So you have half of, so tij then becomes tji, right? Because I to j, j to I. And then here we have f dot kj, and here we have fki. So you can do that because I and j are dummy indices. So you can change I to j and j to I, and you still get the same thing. Okay. And then the next one is already very nicely f dot kj. So I just write it as tij fki f dot kj. And this is equal to pij f dot ij. Okay. Okay, we are almost done. So this is same as half of tji fki plus tij fki times f dot kj, and that's equal to, why don't I on the right hand side I change, let us change, I to k, and j remains j. So if you do that, we have p kj f dot kj. Okay, now comes the, the most important step. See this f dot kj. It is, so each of the f dot kj are independent of each other. So by that I mean f dot 11, f dot 12, f dot 13, they are all independent of each other. You can vary each of them independently. You can think of a deformation such that f dot 11 is something in one, f dot 12 is something in other two, and likewise. Which means that, so what I want to say here is that since f dot kj is arbitrary, since f dot kj is arbitrary, this implies the coefficient of f dot kj will be equal on both the sides. So half of tji fki plus tij fki. That's equal to pkj. Okay, but if you look from here, again, capital E is symmetric, right? Capital E is a symmetric tensor. So capital E dot will also be a symmetric tensor, isn't it? And as I told you earlier, if you have a symmetric tensor double contracted with another tensor, then the antisymmetric part of the other tensor does not yield anything. So this will be basically equivalent to saying that you have some T symmetric double contraction E dot. Because the antisymmetric part of T, when you double contract with E dot, will give you 0. So as far as work is concerned, you can just work with the symmetric part. So you can think of just having the symmetric part, symmetric work conjugate of E. A symmetric work conjugate of E. So this means we can assume T to be symmetric. So if we do that, then we can come back here and you see Tji and you have here Tij. So both are same. So this half is then gone and you have Tji same as Tij. So you can either write it as Tij Fki or Tji Fki, and that's equal to Pkj. Okay, so this is then what is this? F. Can we say that this is same as F into T, and then we take the Kj component, isn't it? F into T and take the Kj component. So this is equal to P Kj component. Or you can say Ft is equal to P, which also implies T is equal to, sorry, Ft is equal to P, which means T is equal to F inverse into P. I'm just done, 1 minute more. So that's T is equal to F inverse P. And if you further write the formula for P in terms of sigma, then what do we have? P in terms of sigma F inverse transpose, yes. So, or T is equal to J times F inverse into sigma into F inverse transpose. And you will indeed see that this is symmetric. Take the symmetric part of it, you get the same thing. And this is called second Piola-Kirchhoff stress tensor. So I'm done here. Thanks for waiting. So the work conjugate of Green-Lagrange strain tensor is this T, which is also called second Piola-Kirchhoff stress tensor. Okay, thanks for staying over time. So this is just one, strain conjugate with Green-Lagrange E. There is another measure of strain. For example, you remember F is equal to RU equal to VR. So U is kind of another strain measure, or let us say half of U minus I, or U minus I could be a strain measure. So what is the work conjugate of such a strain measure? So again, you have to go through the same logic and find out. Okay. Yeah, tell me.
So can you explain that part again where you wrote T double contraction Z dot is equal to sigma double contraction D?
Yeah, over here, no?
Yes, yes, sir.
So actually, it turns out if your Z is green Lagrange, then it should have there should be a J also here. But basically, see what we want to do is we saw that the stress power is sigma double contraction D, right? Per unit deformed volume, it is sigma double contraction D, and J times sigma double contraction D per unit reference volume. And when we want to define work conjugate stress strain pairs, no, then we want to ensure that stress times corresponding strain dot, it should give you the same power as J times sigma double contraction D. So this is a definition how to define stress strain, work conjugate stress strain pairs. So if you choose different Z, you can use this box to find out the corresponding D, the work conjugate stress.